Hello, class. So, what we've been talking about so far has always been about what is the best, right? So, what is the best fitting parameters to get the best fitting model? And we've been talking about everything in a deterministic sense. What I want to do in this course is showcase how this idea of probabilistic programming can extend what we've been doing in differentiable programming. So, differentiable programming and optimization. I want to show how you can extend that to probabilistic programming, so that way you can get accurate probabilistic estimates about what's going on, and be able to start talking about what happens on average, what is the probability that a certain outcome is happening, and all of these types of issues. So, the first place to really start is to understand what is Bayesian modeling and how do you model with probability distributions instead of values. Right. So the idea of Bayesian modeling is to treat all of these variables that you have as a random variable instead of a distribution. If you do want to still have a value instead of a distribution, you can use a Dirac delta distribution, which would mean that 100% of the probability is for a variable to have a given point, right? So you can mix the idea of having points and distributions, but this generalization really is about now we have distributions. And so, as a starting point to really understand what it means to have a variable as a distribution instead of a number, we can talk about or think about having the linear model, which is f of x equals ax. And now let's ask the question of what happens if you have variable a be a distribution instead of just being a number, right? So in a Bayesian sense, the value of a is a random variable. So a random variable is a variable such that every instance of it is taken from a probability distribution. So that's what this notation says. This notation says that z is follows the probability distribution f of y, which means that the probability that z takes a certain value in a set omega is given by the integral over this probability distribution. Right? So and what we're going to be looking at in terms of this lecture then is what does it mean for a variable to do, to take a probability distribution, and how can you actually compute with that, right? Because some of you might know how to deal with those kinds of variables in terms of theory, right? And we can showcase things on whiteboards on how to handle such variables, but like this is something that we want to compute with now, right? We want to be able to compute with this probability distribution, and we want to be able to optimize probability distributions just like we were numerically optimizing values. And that's what probabilistic programming is going to be all be about. So, for an example of a probability distribution, let's say that z is scalar, um, then the probability that z is within, between the values of 0 and 1 is just given by the integral from 0 to 1 of the probability distribution, right? So, um, yeah, so this way of writing it is more general, right? Because your domain could be, four-dimensional space, and so this could mean a four-dimensional integral. But in a sense, what we're really talking about is if you want to know if you want to know the probability that z is within a given region, it becomes down to taking integrals. And that this means that the probability, if everything is about continuous probability distributions, like a normal distribution, the probability that a value equals zero, is zero in that sense because the integral from 0 to 0 is zero of any measure function that's not it doesn't have like direct deltas, right? So um, that's where I'm saying that you can have this idea of a Dirac delta be inside of the integral, so that way you can have finite probability of being at given points. But for the most part, this probability distributions have zero probability of being at any given point, but non-zero probabilities that a value is in a region, right? So we want to figure out the probability of hitting these regions given the fact that any given point is unlikely, right? Like every single point you take from a probability distribution has zero probability, but when you build a distribution about those points, that is still a well-defined sense. So discrete probability distributions can be handled as quantities and measures under the integral, right? So if you have a discrete distribution, like you have probability of 1/3 of being at one and 1/3 of being at two, you can say that your probability distribution is f of y equals the delta um, of y minus one with a probability of 1/3, and uh, 2/3 probability of being at delta y minus 2, because if you remember your properties of Dirac delta, right, the integral of from so the integral from 1 to 1 of f of y dy, if it has a Dirac delta, is the integral from 1 to 1 of this other term is going to be 0 over that whole domain. This is 1/3 Dirac delta of y minus 1 dy, which equals just 1/3, right? So this is just the property of the Dirac delta function. If you're not familiar with deltas, Dirac delta, they're not actually functions, they're distributions themselves, and you can read all about them. But essentially, this is their definition, that when you integrate a Dirac delta at y minus x, it has the value of the coefficient in as its solution at that point. That's precisely the definition, actually. You define how it works by its integral. So if you want to represent a discrete probability distribution in terms of a measure over this kind of space, then you can define it via these Dirac deltas. It's not actually a function anymore. That's why these objects are more general than functions in some sense, because in some sense the Dirac delta would be zero everywhere except for one point where it's infinity, but integrate to a value one. So it's not really well defined as a function, but it's well defined in another sense that we won't discuss in this course. So given a representation of our values, right, where we're saying a, for example, a could be distributed like this, which means it has a 1/3 chance of being the value one and a 2/3 chance of being the value two, or we can more generally say that, for example, f of y equals e to the minus y squared divided by 2, which is a representation of a Gaussian, which means that this is a normally distributed random variable. So we normally call this a normally distributed random variable with mean 0 and variance 1. So this is your standard Gaussian, standard normal. So we can say that we have discrete values, or we have normally distributed values, and all these different values in terms of these continuous objects, which we call probability distributions. And given a representation of a variable, so we can say if A follows a normal distribution and X is something that's known, then what is the probability distribution of A times X? And so this induces a probability distribution on all functions of A. If you have g of A, if you have g of A as some value where uh, where A is something that is given by a probability distribution, f of y, then g of A is given by a probability distribution, which yeah, I mean, you can look up the formulas for how you do the change of variables. Essentially, you have to do it's f of y times the Jacobian of so dg d dg dA at some point, and the reason is because this comes from the integral formula. So if we want to do the integral formula for change of variables, so we want to talk about the probability distribution of g of a, then we would do the change of variables formula, which is where the Jacobian comes in. So you go back to calculus, and you can derive this quite simply. So if you really want to know what the distribution of g of a is, using these analytical integrals can be difficult, right? It's what you'd use in theory, but what if you just have a computer? Um, then what you can use, if you want to know the probability distribution of g of a, you can use what's known as Monte Carlo sampling. And the way to think about it is, on the discrete example, what you can do is if you have this, a so let's say you want to know the probability distribution of a squared, um, given that you have this probability distribution 1/3, 2/3. What you can do is you can take samples of a. 1/3 of those values will be 1/3, um, or one of the third of those values will be 1, in which case that 1/3 of the values 1/3 of the values will give you the value of 1 squared, which is 1, and then 1/3 of the values will give you, or 2/3 of the values in the sampling process will be 4. So let me say that again. Let's say g of a is equal a squared, then a squared it has a probability of this if the probability distribution of a was this. Right, so why would that be the case? Well, 1/3 of the time a equals 1, and so 1/3 of the time a squared equals 1. 2/3 of the time a squared a 2/3 of the time a equals 2, and so 2/3 of the time a squared equals 4. Right, and so that's what this statement is that if our probability distribution on a was this, then we can write down that probability distribution quite simply. Now, how can we do that on a computer? Well, we could just sample a whole bunch of values of a, right? So we can say randomly take values where 1/3 of the time it's equal to 1 and 2/3 of the time it's equal to 2. And so if you take a bunch of samples and then you put it through this function g, then what you'll probably find is that you'll get this probability distribution found not in terms of analytical formula, but 1/3 of the values that you have in your array will be 1, and 2/3 of the values will be 4. Right? And so this is a very general sense for how to push forward probability distributions into other functions, right? Because if you want, if you say that a is given by this probability distribution, and then you want to square it, well, someone sat down and derived this before and said that this is a chi-squared distribution, where chi-squared distribution follows some really fancy PDF, which is given here, where you have a gamma distribution, right? So this gets very complicated really fast, and it's not necessarily easy to know just by squaring a how would you change this probability distribution, right? It doesn't mean that you square the probability distribution, because actually the probability of getting a value that is very large is going to increase, because if you have 2, that becomes 4, but also the probability of having very small values increases as well, because if you had 1/2, then squaring it would go to 1/4. And so it's a very complicated change to change from the distribution of a to the distribution of a squared, but it's fairly simple to do on a computer, right? Because if you so let's actually do this, and let's actually do the simplest case in practice here, right? Which is so let me get something going here. So the simplest case in practice would just be to say let's do a direct calculation of that value. And sorry, I forgot to get a window ready here. So if we want to do direct computation of that value, so let's say that we have the way that you get a normal distribution, our normally distributed value in Julia is just through the rand_n function, which is similar to most programming languages. Right, so this pulls a value from that distribution, and now we can say I want 1,000 of those variables. So this is my discrete version of A, right? So it's, in some sense, it's a representation of this more continuous object, which has infinitely many, poles from it. I can represent it with just 1,000 poles. And then how would I know what a representation of A squared? Well, I can just do A dot, caret squared. And this is a representation of all of the possible, a squared values, and where you can see that, for example, there's a 0 probability of having things negative. There's a high probability of having larger numbers than what we had before, but also smaller numbers. And so this is a pointwise representation of that probability distribution, where if you take infinitely many samples, in some sense it becomes a better and better representation. So okay, so this is the idea of Monte Carlo sampling, right? So it's the process of just sampling variables and computing outputs, and what that will do is it'll push forward probability distributions. So if you have a probability distribution on the inputs, a Monte Carlo sample will give a representation of a probability distribution on the output function just by sampling inputs and then and that gives you appropriate samples of the output. You can prove then that these samples that you're getting or the numbers that you're calculating are the probability of getting a specific number or getting in a region of numbers is exactly equal to the theoretical probability on that on g of a. And so therefore this is a valid way to compute the push forward of a probability distribution in terms of specific values. um, so you can then do this in a multivariable sense. You can say I have a probability distribution over x, y, z, and you take samples of 3D space of x, y, z, you push them through your program. So this is a very general sense for how to um, do computation with probability distributions. So let's take a look at a quick example, right? So we've been looking at differential equations a lot, like the Volterra equations. Here is just a simple ordinary differential equation, which is defined by values, right? So let's say we want to do computation now with probabilistic estimates, so that way our variables are Bayesian, these random variables. So let's assume that we have thetas that are random. So instead of using parameters like point values like 1.5, 1.0, etc., we can have our distribution. We can have um, our parameters be random numbers where we can represent them, for example, with this nice library distributions.jl, right? So we can actually say my thetas are a uniform random distribution from 1/2 or 0.5 to 1.5. So what you'd represent that with is so u of 0.5 1.5 is the distribution, which is given by the function that is fraction. Right, so the distribution function for this would be that you have, so all probability distributions integrate to the value 1, and so this is going to be, let me write this in its more general form. This is going to be 1 divided by b minus a um, if y is, sorry, if y is in a to b and 0 otherwise. Right, and why is this a probability distribution? Well, if you integrate this, then anything that's outside of, so the integral of, uh, let's say this is h of y, which is equal to this. So the integral of h of y dy is equal to, well, everything that's 0 can be discarded. So we have a to b, we have a to b of 1 b minus a, which is equal to this constant 1 divided by b minus a, integral from a to b of 1, which is equal to b minus a over b minus a, which equals 1, right? So this is the reason why I'm doing that is showing that there's a 100% probability. So this is a valid way to represent a probability distribution, and this is the commonly known uniform distribution, right? So if for any of these other distributions, you can look up what they mean. So for example, beta distribution is a distribution of values between 0 to 1. A normal distribution is, as we described up here, and a gamma distribution is, uh, uh, it's a bit more complex. So I'll spare you the details on how to define the gamma distribution, and you can just take a look at it in here. Right, so it's defined by the gamma function, and then there's a lot of other details in the definition here, but it's another classic distribution function. So here, and what I'm saying now is that I have a parameter, which is a uniform distribution. I have one that's a beta distribution. I have one that's a normal distribution. And I have another that's this crazy gamma distribution, right? So now I want to do computation with this, right? So I made the assumption that my parameters follow these distributions, and we'll get into how we can fit distributions in a second. But let's assume that I know these distributions just analytically, or I've done some measurements and these are nice approximations. And now let's say I want to do computation using these distributions. What I can do is I can sample values from the distributions. I then solve, so here I sample one random set from the distribution. I define the ODE by that parameter set, then I solve it and I plot it. All right, so that's just one value, though it's not representative of the full probability distribution, and this happens to be one value where it looks like the cycle length in the Lockville-Terry equations is much larger than maybe what the average value is, or maybe that's not an average, right? So is this something that's indicative of the average, or is this an outlier case? Right. If we want to know this, then we need to get the probability distribution on the ODE solution, right? We want to go from the probability distribution of the parameters to the probability distribution of the ODE solution. Now, since we don't even have an analytical solution to the ODE solution itself, this would be fairly hard to do analytically. But if we do this Monte Carlo sampling idea, then it's fairly simple to get a draw of this probability distribution. So here I'm showing that you can make use of what's known as the Ensemble Interface in the differential equation solver. This will automatically multi-thread it. The way that it's doing this multi-threading is actually fairly similar to what you did in the first homework on the multi-threaded and parallelized dynamical systems. And so I multi-thread a process where every single time it samples from the random distribution. And then I say do this 1,000 times and plot a summary of the ensemble, right? So you have 1,000 different ODE solutions. What does the probability distribution look like? So here what it's showing is that on average, you have something that kind of loses its cycle behavior for this set of parameters. And so here is the average solution, and here is the average solution of the other variable. So this is actually, quite indicative of the average solution kind of for this b value. Now having the second spike happen within this time frame is actually not very natural. And seeing multiple spikes like this is essentially is unheard of for the parameters that are possible in the distributions that we gave here. The reason why it's different is because this beta distribution gives you a probability of between 0 and 1, and so the point estimate that we had here is actually an extreme of this probability distribution and very unheard of. So in general, this value is much smaller. And then because it's much smaller, you're actually getting much larger cycle lengths. There's probably on average a spike that's outside of this 10 seconds. And, so you can look into the probability of the ODE solver solution like this and start to ask a lot of questions. So that's all about push forward, right? So if you knew the probability distributions, how would you push them forward to get a probability distribution on the output? And so this is where a lot of Bayesian neural networks and Bayesian scientific machine learning is coming from, where you say if I knew the probability distribution on my neural network's weights, then I can give you a probability distribution on the fact that on the probability that this image is a 1 versus a 2 or a cat versus a dog, or I can give you the probability that that the PDE solution is in a given range. But this all assumes that I know the probability distribution, right? So the what we had to go to before was in the process of incorporating data into our models, right? What we started to do is we said we have a model, let's estimate what theta would be and find the best theta from data, right? Now let's think about this in the probability sense, right? So we want to solve the problem that is given this model, find the probability distribution which best represents the data that I'm seeing. And this is the Bayesian estimation problem or probabilistic programming. So there's a few things that you can do, right? So if you want to do an estimate, so the first thing that we can do is say estimating a probability distribution is going to be much harder than estimating one point because a probability distribution is a whole function, right? Um, so let's try to do something a bit easier and say, can we estimate, can we just estimate what the most probable, can we estimate what the most probable parameters are from data? So let's take a look at what that means. So the way to come up with a estimate for the most probable parameters is to use Bayes' rule. So Bayes' rule, also known as the flip-flop rule, is how you'd be able to calculate the probability of having a given parameter theta given the data that you've actually measured in the lab. And it's called the flip-flop rule because you get this the probability of having theta given the data by using the probability of having the data given theta and what's known as the prior distribution p of theta, right? So this prior distribution, the way to think about it is like the initial condition of a optimization, right? So we have to have an initial set, an initial distribution, and then we go from the initial distribution and we move it towards something that is more likely for our data. So this is called the prior distribution, and we need to have it as like an initial value in our estimation process. Um, but now what is this object, right? So it's called the likelihood distribution. And the way to calculate the likelihood distribution is to take your parameters theta, run it through the model, and then define a distribution on the model's outputs. So what you can do is you can say, for example, that what is the probability that of having data all the way up here, given the model is all the way down here? Well, that's what you'd say is your measurement error. Right? So if you went to the lab and you did your experiment 5 times, and you see that on average you have on average your values are changing by ±1, then you might want to have a normal distribution that says if the output of my simulation is right here, then I should think about this as like ±1 in terms of the probability of seeing given values. And so that distribution on the measurements is what we call the likelihood distribution, and it's capturing the possible measurement noise in our problem. And now the other thing to make note of is that there's a scaling factor on the bottom here. So remember that our probability distributions always need to integrate to 1. And so all that we do is we take this value, we integrate it over all space, and we divide it by that value. That way, if the full integral of this function was 3, then we divide by 3, so that way the integral always equals 1. So this is just a scaling factor. So don't worry about the denominator too much. It's really the numerator that's important. Um, and the reason why we call this a measurement distribution is because it's just a distribution on the output, right? So it's not taking into account probabilistic factors in our simulation itself. So for example, if we had a stochastic differential equation, then solving the differential equation would be something that's probabilistic itself. And so we can have probabilities in the process, but we're going to ignore that for now, right? Because the likelihood function is just a probability on if your simulator had this output, what is the probability of actually measuring another output? Um, this you have to make a choice for what this measurement distribution is, and normally what you want to do then is you want to say, um, or a very common choice is the normal distribution, where you say f of x given a mu and a theta, where or mu and sigma, where mu is the mean and sigma is the variance, is equal to 1 divided by sigma, sorry, square root of 2 pi um, exponential to the minus x minus mu squared, right? So this is just a very standard choice for what this probability distribution would be because it's the standard old bell curve. So what we're saying is that, so what we want to say is we want to say that the most probable outcome of the data, given what we're seeing, the output from the simulation is, right? So if we had to guess what our data points would be given our simulation, we would say that the most probable point is whatever our simulation is spitting out. And then there's some variance around that. So there's some probability that it's actually up here, but it's most likely what the value that we're predicting, right? Like if our model is supposed to be predictive, then we take the most likely prediction as the point estimate output of our model. And so what we'll do then is we'll say that let's say we have a differential equation mu prime equals dot dot dot, right? So what would our likelihood of seeing a data point at a value x be given the output of our model, where our model is a ODE solution given a set of theta, a given set of parameters, right? Well, we would say that the probability distribution should probably be something along the lines of the probability of seeing the data at a value x given um, the probability distribution is centered around the output of our simulator with some chosen variance, right? So we have to choose here some kind of some probability of actually being further away from the simulation, and we'll see the effect of that choice of variance here, right? But we've made two choices. We said we're going to choose a normal distribution, and we're going to center that normal distribution around what our simulator says is the most probable value, and we're going to put a probability distribution sigma around that. And so, if you actually measured in the if you actually measure that your data is here in the lab, so data equals 4 at a time 2, then the probability distribution that you would look at is, at time 2 from your ODE solution, you want to look at the probability of having a data point equal to 4, right? So and then if you stick this into this function here, where you make a choice of the variance like 1.0, this will spit out a value, right? And that value is the value that you'd put in this likelihood function. So here you can see everything coming together, right? So we made a choice of the distributional form. We said it's a normal distribution. And then what you would do to calculate likelihoods is you'd solve your ODE for a given theta. You would then put the normal distribution around your ODEs, so around your ODE's prediction, with a given randomness around it, and then you ask yourself, what is the probability of seeing this data point given this probability distribution? And then this will spit out a scalar. So that's how you calculate the probability of seeing a data point given your theta, right? You assume your model, so you assume your ODE, and then you assume a measurement noise distribution around it. And once you've made those two assumptions, then you can compute probabilistic estimates. So let's actually follow this thread where we say, let's assume that our probability distribution is this. Let's assume that we have a given theta here that is some fixed value. And let's see what happens if we have some simulator here that is telling us what to do at given values of I, and we have data points at the different values I. Right, so if we have a bunch of data points, d sub I equals, so we have a data at t sub I, which is at a value of x sub I, then our probability distribution on the data, given all of the probability distribution on all of the data, given the thetas, is the probability of seeing that xi, of x1, the probability of seeing x2, and the probability of seeing x3, and the probability of seeing x4, right? So how do you put these probabilities together when you have and? So what is the probability that the first coin flip is one or is heads and the second coin flip is heads? Well, you take the probability of heads, multiply it by the probability of heads, right? So whenever you have the probability of ands, you multiply. When you have the probability of A or B, you add them together. So here we want to do the probability of seeing x1 is a given value and the probability of seeing x2 is a given value, and etc. Right. So this notation here, this capital pi is the prod symbol, which means I'm going to take I'm going to take the product or multiply all of these different values. So I'm going to multiply over all these different values, where the value is the probability of seeing xy or xi, given that my simulation is spitting out t sub I when I run it with parameters theta, with the choice of this sigma. So that's what this is saying. Let me run through that one more time. The probability of seeing my data given a assumed choice of theta is the probability, or is the product of all of the probabilities over every data point, where at a given data point, it's the probability of seeing that specific piece of data, given the fact that, with a theta, my ODE solution assumes that it predicts that the data should be all the way down here. and I have a sigma that is then defining how likely it is that my ODE solution is incorrect. Right, so this is that likelihood distribution, which I'm saying here, right? So if I had n different data points and I'm trying to fit my ODE to it probabilistically, this is the formula that I would have if I assume that my measurement noise is normally distributed and my measurement noise has some constant variance across it. I think this might make a little bit more sense when we finish up this distribution, this derivation here. Right. So normally what we want, so one way, so dealing with products is kind of difficult, especially dealing with products of exponential values, right? So whenever you see exponentials and you want to do multiplications of exponentials, it usually means that an easier way to do things is to look at the log, right? So this is just a scalar, right? Remember, you with our data, when you put in a parameter value, you run your ODE solution, you calculate a bunch of these scalar values, and you multiply them all together, and that gives you the scalar value for this probability distribution. But what's an easier way than doing a whole bunch of multiplications is it's usually easier to do a bunch of additions. So what we want to do then is we look at the log um, of this posterior distribution or likelihood function. And so this is so common that it's actually called the log likelihood. And whenever you take a log, you turn all of your products into summations. And so this is just going to be the log of our probability distribution at each of these points, right? This just comes from taking a log of both sides. And now, if we assume that this is a normal distribution, we assume that this is the normal distribution, let's actually just stick that value in, right? So what is the log of this function right here? Well, it's going to be, um, you know, remember that the log of a times b is just the log of a plus the log of b, or actually, so this is a so this is a scalar multiple, or yeah, this is scalar multiples. So then we can pull out the scalar, and uh, so let's first start by pulling out the scalar and adding it to the other value. So let's actually do this step by step. So let's plug in. We have the log of this, which is equal to the sum over I of the log. So this is the rule where we split it out by multiplication. Right? And now this is just a constant, so let's get rid of it. So we have fraction. So if we had n data points that we're looking at, then we would just have this same value show up n different times. So we could just pull this out of the summation and say there's, it's n times that constant plus, or it's n times the, actually, sorry, I think that there's an error in these notes. It's going to be n times the log of this constant, sorry. Plus a sigma of log of x of this value. What is the log of the x? What is the log of the exponential? Well, that is just the value inside of it, right? So that cancels out. We have the sum over I of this. All right. So let's say let's say we want to choose we want to choose sorry. So instead of having mu here, right? So so let's say we want to have these normal distributions centered around our 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 simulation, right? Then what we would do is actually this mu would be the simulation point, right? So I plug this in for all these different mu's, mu, mu. Then what this is actually saying then is if we want to choose theta such that we maximize the probability of seeing the data given the given theta, where the measurement distribution is the normal distribution, then it would just be the same as saying, find the max over theta of this expression of the log likelihood, which, right, well, it'd be the max of the likelihood, but the max, log is a monotonic transformation, and so if you know the maximum value or the point theta, which gives you the maximum probability, is also going to be the point theta, which gives you um, the maximum log of the probability, right? Because if the logarithm is always increasing, then if you log all your values and you found the maximum, that's still going to be the maximum in the log. Theta. Oh, so let me say argmax here. So the argument theta that maximizes there is also going to, so we want to find the theta that maximizes this assumption, which is the same theta that would maximize this, which is then the same theta that would maximize the um, this, because we just derived that this is the log of our probability distribution when we have a normal distribution. But now, since this is just a constant, the theta that would maximize this is equivalent to the theta that would maximize the function that doesn't have this scalar factor, right? Because if every single point is added by the scalar factor, then it does, if every single theta has this value added, having this scalar added to it, then you can pull everything back down by that same scalar, and you will still have the same theta that maximizes this function, right? Which means that the theta that gives you the maximum probability of seeing the data given the theta is the theta that maximizes the sum squared error, right? Because this is the sum of the error, or the difference, the square difference between our data points and our predicted ODE outputs. So what this means is that, the probability, if you want to choose theta that maximizes the probability of seeing data given theta, where we assume a measurement noise is the normal distribution, then this would be equivalent to maximize, or to uh, minimizing the sum squared error, right? Because we want to maximize the minimum of, or maximize the negative of the sum squared error, which is the same as minimizing, right? So you can, if you maximize f, then it's the same as minimizing minus f, right? And so we can do one last change here and get rid of this minus sign. And so this is going to be saying that, doing this process of maximizing the probability is equivalent to minimizing the sum squared error. And this is where we then arrive back at what we were doing before, right? Because everything that we are doing before in terms of point estimates was, let's take the data that we have and find the theta that give you we find the theta that gets as close to the data point as possible, right? So if we then said everything with probability distributions, but we choose this normal distribution as our point, and then we just say we want to find the theta that maximizes the probability, then the theta that maximizes the probability given a measurement noise distribution of a normal distribution is exactly the same as the value that minimizes the sum squared error. And so that's where how these two approaches kind of come back to each other, right? So if you just wanted the best point estimate and you made a few other assumptions to your problem here, then it would be equivalent to having just done the optimization procedure that we did before. But you can see now that there's a bunch of other choices we can make, right? So for example, we can try to estimate this whole distribution. We can use distributions which are not just the normal distribution. So first of all, let's look at what happens when we do a small change to that distribution, right? So let's say we have so let's say we have, at each data point we actually have a mu I sigma I, right? So what would that mean? What that would mean that we now have a different measurement noise around each of our data points. So we're more certain about some data points than we are about other data points. If you run this same procedure, what you'll find is that with this choice of measurement noise, so with this choice of measurement noise, what you end up with is an expression where now everything is the same, except now everything is the same, except now you can no longer you can no longer do the simplification because each of these theta are different, right? So you can no longer simplify like that. Also, each of these theta points are different. But if we run this same argument again, then the point which maximizes the probability. Let's actually step by step change this, or step by step fix this back up. So the point that would maximize the probability of the data given theta under this distribution, where each of the data points has a different, variance or different amount of uncertainty around it, would be, first step, you do the argmax of the log, which is the argmax of the log, where I can no longer use the simplification. But it doesn't necessarily matter that I can't use that simplification because this is still a constant, right? So the argmax of this term is still going to be the argmax of just ignoring the constant, where now I have sigmas on bottom, sigmas on bottom. And so what this is telling me is that the the way to do this problem, the maximum probability estimate, given that we have different amounts of uncertainty at each data point, all you do is you would do a sum squared error. You'd minimize the sum squared error where you are weighting the terms in proportion to the amount of uncertainty you think there is in the variance, right? So once again, so what this comes down to is saying that if the non probability way of doing this would be to optimize data such that the data at I minus minus the ODE solution, where now what I'm going to do is I'm going to sum this up over every data point. But now I'm going to say, well, I have a factor here, which is sigma sub I, my uncertainty of the data point. What this is saying is that the optimization way of solving this problem would be to find the theta that minimizes this expression. So making your measurement distribution have a different variance at each point, so having a different amount of measurement noise around each value is equivalent to doing an optimization where you're just weighing the different points, where you put more weight on the points that have less measurement noise. And that makes a lot of sense. So you can start to see that this is a very much more generalized sense than from the optimization, right? You make choices about probability of seeing certain things in your data, and that naturally gives you different ways to do this optimization. Now you can directly, you don't have to bring it all the way to the maximum likelihood argument. You can necessarily stop right here, right? So you can say the way that I'm going to computationally do this is I put a theta in, I get an ODE solution, right? I get this ODE solution, and then at each data point I evaluate this um, I evaluate this whole expression, right, which is my plugging in my ODE solution as the mean into my probability into my measurement distribution. I sum all those up and I take logs of them, and that is a way to calculate the log probability. And so you can this is what you call the maximum likelihood procedure, where you're performing optimization directly on this expression. But it just turns out that maximum likelihood of this expression, when you assume that your measurement noise is normal, is exactly the same solution as optimizing the sum squared error. So that's a nice relationship between the two approaches then. So what we want to do with probabilistic programming is you want to go beyond this sense of point estimates, right? We want to be able to find the probability distribution for our values. So at least this is telling us that using Bayes' rule makes sense, right? Because if we use Bayes' rule with a small subset of, with some certain assumptions, then we get exactly what we're doing with optimization before. Now let's extend beyond that. So let's say we want to do a Bayesian estimation of the posterior distribution. So we want to numerically find out what is this distribution, not just not just the highest probability point in the distribution, but let's say we want to find the entire distribution itself. Because we want to have a probability, we want to in the end be able to do simulations which have the uncertainty associated with it. So we don't want to just find the most probable value, we want to find probability of all values. So in general, there are two approaches to find full distributions, right? Because we're looking for functions. There's two ways to do. So remember that I mentioned that when we were I mentioned that when we were looking at how to do uncertainty distributions, I mentioned that I mentioned that you can represent these uncertainty distributions by taking samples of them and then pushing samples through programs, right? So one way to be able to estimate what this posterior distribution is through a sampling approach where you're taking random numbers from the prior distribution. So you take random numbers from these distributions and you come up with a sampling approach such that you get an array that is sampled according to this output. And so this is what Markov chain Monte Carlo methods are doing. They're doing a sampling process on these values in order to get a array which is representative of the output of the solution. So you can use a sampling approach, or you can use what's known as variational inference, which is a more direct calculation on the probability distributions. So let's first start to ask the question of, if I have if I have a given set of a's and I have an a squared, right? Um, this is a representation of a probability distribution, but probability distributions are these functions, right? So how do I recover what that function is from a given discrete set of points, which are kind of have probabilities according to some given function, right? So let's say you had x was a normal distribution, you took random values from it, and you just did a scatter plot of it. So if I have that this is the normal distribution, which has a mean of 5 and a variance of 1, then most of the points should be around 5. And then I should have less points as I get away from 5, right? So there's like a bell curve which is centered around 5 here. So how do I take this discrete set of points, right? And where I kind of see that there's more points here than there is out here, how do I take that and recover the probability distribution? One way to do this is with a histogram, right? So a histogram is where you count up the number of points here, like the number of points between 0 to 5, number of points between 0 to 5 to 6. And you'll see that this histogram is a way to turn this given set of samples back into probability distributions. And if you take more and more samples, this histogram will get closer and closer to the true probability distribution. So histogram is kind of like a discrete way of turning discrete points back into probability distributions. Right, so you're then getting a discrete probability distribution, kind of in the sense of what we were talking at the early part of this lecture, right? Where you then get a probability of being in between, 4.1, 4.0 and 4.1. You get a probability of being within 4.1 and 4.2, and you can then interpret this probability distribution, as something that has these little jumps, but it is a representation of a distribution. But how can we do this in a continuous sense? So this is something called a kernel density estimate, where it's essentially using a smooth bending approach. I'm not going to describe it in too much detail, but it's looking at the density of points in a given range, and then it's passing over the points, and it's then running essentially a smoother over that. And so if you take enough points, what you see is that your kernel density estimate, which is the blue here, um, the orange is the real probability distribution. If you take enough points, then this kernel density estimate is able to give you a continuous function, which is a representation of that probability distribution. But essentially, it's kind of like a smooth version of the histogram, It's a smooth, continuous histogram. So if I did wanted to find what the probability distribution is for a squared, given that the input or given that a is a normal distribution, I can do the histogram on on a squared, right? I can take values of a, I can square them all, and then I can take the histogram of this output, and that would give me a representation of this probability distribution. And if I want that representation to be continuous, I can do a kernel density estimate. So what this means is that we can use the sampling approaches to be able to recover probability distributions, right? So all we need then is we can use these sampling approaches to be able to estimate our posterior distributions, and we can then always go back to functions by using these kernel density estimates. So now that we need is we need a way to be able to sample from this probability distribution, right? We need to be able to sample from the probability of having theta given the data. And the way that Markov chain Monte Carlo methods work is they come up with a sampling process for probability of theta given data by first you assume a prior distribution, right? This assumption needs to be made. It's the initial condition of this probabilistic optimization process. But the way that these Markov chain Monte Carlo methods work is they give you a sampling method for this likelihood function. You can ignore the denominator because it's just a scaling factor. And so all we really need is we need a sampling process on what is the probability of seeing the data given our theta. So there's many different methods for doing this. The simplest one is the Metropolis Hastings algorithm, where what you do is you say that the probability of the instead of trying to get the probability directly, what we want to do is we want to only look at the ratios of probabilities. We want to look at the ratio of seeing the probability of having our actual parameters being x sub I, the ratio of the probability of having parameters x sub I versus the probability of having parameters x sub j is to just divide those two expressions given by basis rule, right? Um, what happens to this other term in basis rule? Well, remember that this is just a scaling factor, and so since we divided by the scaling factor twice, the two scaling factors canceled each other out. So the scaling factors cancel, and so the ratio of the probability of seeing these thetas given the datas is essentially the ratio of the multiplications between the prior distributions and the likelihood distribution. So the Metropolis Hastings algorithm is the following. So given we need a starting point. So let's say we start with a given value of theta, right? We say that theta equals with some assumption. So the way that you come up with the next choice of theta to put into your simulator is you take a theta from a sampling algorithm. So the sampling algorithm should be symmetric. So you should say, so a standard one is to take a normal distribution around your current theta. So let's say we're doing it on here, right? So what we do is we'd say instead of so we have A is distributed as normal distributions 0 to 1. We have that we want to find the distribution of A squared, right? So what we do is we'd start with a value A equals 0.5, right? So we just choose A equals 0.5. Now we need a sampling algorithm. So what we can do is we can say like my next A is equal to my previous A. So I want to center it around my previous A, but I'm going to have, I'm going to take some randomness around it. Right, so if A is equal to 0.5, my sampling algorithm might say check this point next or check this point next. Right, so it's a random point that it will check next, but it's at least centered around our current value. Now what I want to do is calculate the ratio of the probabilities. The ratio of the probability of A versus the ratio probability of next A, right? So in the sense of our ODE solution, this would be we would we would solve the ODE with the two sets of parameters, and this ratio is the ratio of the probability of seeing the data given parameter 1 versus the ratio of seeing the data with parameter 2, right? So if the probability, if the ODE solution's output with parameter 1 is closer than that of parameter 2, then the denominator is going to be more likely, it's going to be a higher probability than the numerator, right? And this is going to be less than 1. But if our next set of parameters is closer to our data points, right, then it's going to have a higher probability of, have seen that data given the thetas, right? And so this probability ratio is going to be greater than 1. And so A is just going to be we clip it at 1. So we say we use the ratio of the probabilities, but if our new point is more likely than our previous point, then we just take a probability, then we make A equal to 1. So A is from 0 to 1, where if new parameters are more likely, our new parameters are more likely to give us the data, then we have a probability 1. If our new parameters are less likely to have given us the data, then we use the ratio of our likelihood functions. This simplifies quite a bit, right? So if our G is symmetric, so if we have a symmetric distribution function, which means that we center it around our point, and the probability of seeing the next data given the last one is the same as flipping those around, right, which is is a nice assumption to make. Then you can then this ratio, you can discard the sampling point. So that's just a simplification here to get us to so A is either the ratio of these probabilities or it's just or it's 1. So now what the key to the Metropolis Hastings algorithm is this next part, right? And it's that accept this next value with a probability of A. What does that mean? So I have A1, let's say I have A1 equal to this, and I have A2 or A2 or my proposed next A is this value. Right? I'd take that parameter, I would stick it in the simulator. If that has a higher probability, or so if this is closer to my data, then 100% of the time I will accept this as A2. So A2 equals next A is what I would do. And I would then move on to my, next A again is equal to A2. So I'd sample again and I keep on doing this, right? Well, what happens if you get a point that has a lower probability, of it having the data? Well, you don't just get rid of it all the time. The probability that you take that value as your next parameter point is going to be um, essentially that probability that is given by the ratios, right? It's a value from 0 to 1, so you use that probability. And so the interesting thing about Metropolis Hastings algorithm is that if you use this algorithm, so like I say, the theta that goes into my ODE is 0.5, and then I calculate it, I run that, and then I find what my next proposed theta is by doing the sampling process. Um, I find my next proposed theta by using the sampling process. Then I check the ratio of the probabilities, which is essentially the probability of seeing a data right here given this output. And then if I have a different theta, I have a different output, the probability of seeing the data in the same spot given the ODE is now closer, right? Then that has a probability of 1. Also take that theta, and if I move further away from the data point, I don't zero it, but I actually have a probability of still accepting that theta, right? So you can, most of the time, then, this is a biased process, which is most of the time you're going to be moving closer and closer or to better thetas that are better fitting your data. But it's also allowing you to take thetas which are doing a little bit worse. And the reason is because you want to get a full probability estimate. And what you can prove from the Metropolis Hastings algorithm is that using exactly this factor is correct, such that if you run this process for a lot of samples, then the output array that you have for theta 1, theta 2, theta 3, theta 1000, it converges to the probability distribution of p of theta given data. So it seems like a little bit like magic, but let me explain that by, so here I want to go to the Turing.ml. Inside of here there is a tutorial, which is the tutorial for the tutorial for Bayesian differential equations, which essentially showcases this, right? So let's say we take data from the Lockable-Terra distribution. So here I'm just solving a Lockable-Terra distribution deterministically to get a set of ODE data, right? Let me skip over this one. So what I can do then is I can say I need to have prior distributions, right? Because you always need a prior distribution for this process. So what I'm going to say is that, well, here are my assumed prior distributions. I'm also going to have to put a prior distribution over the sigma that shows up in my measurement distribution. And now how do I calculate the likelihood? Well, I'll take parameters which are sampled from distributions. I solve the ODE with those parameters. And then I say, now let's make my likelihood is a normal distribution which is centered with mean around the ODE solver's output with this sigma as the randomness, right? So that's this process. I'll go into what nuts is. This is the no U-turn sampler. It's a little bit better than Metropolis Hastings. But essentially what you do is you get a whole chain, right? So it's going to run this Markov chain Monte Carlo process. You get a prediction of what is alpha 1, alpha 2, alpha 3, alpha 4, where over this whole chain, you get a probability distribution over what is the most likely value of alpha and what are all the probabilities of having different alphas given the data that we have, right? So given this data that we generated where we know the true parameters, right? Um, let's do a probabilistic estimate for what the probability distribution is on alpha, probability distribution is on beta, probability distribution is on gamma, right? So that's what Turing spits out, and it starts by giving you a few things to really try to understand the probability distribution. So it says, the probability distribution around theta, around alpha, is, so if I wanted to understand, um, here I have a bunch of samples of A, I want to understand what is the probability distribution of A squared. The first thing I can do is I can look at, what is the mean of A squared? What is the mean of A squared? What is the variance of A squared? I need to be using statistics. Right, so the mean of A squared is 1, the variance of A squared is 2. And so this is essentially what it's telling me, right? So this would be the way to represent the distribution of A squared is trying to tell me what is the distribution of alpha given the data? What is the distribution of beta given the data? So these are distributions centered around 1.5, 1, 3, and 1, which is not too unnatural because the way that I generated the data is an ODE solution where alpha equals 1.5, beta equals 1, delta equals 3, and gamma equals 1, right? So it found that the best distributions for representing our points are distributions where it's where the mean values are exactly the values that were used to estimate to generate the data. But this also has some randomness in there, so it's telling me like, oh, this is the amount of randomness, the standard deviation around that point estimate. And then what you can do to understand that solution is to look at what's known as the chain plot. So if you plot the chain, what this is telling us is so this is the actual steps of, so you have theta 1, theta 2, theta 3, etc., stepping over this Metropolis Hastings process. So what this is showing us is that this is actually for a slightly different one, sorry. But the way to interpret this is, you're actually looking at, the first value of the first value of A was 2.3, and then it chose to use a value of A of like 2.35, then it chose to use a value of A of 2.36, right? And so it's showing you that it did this whole walk over a whole bunch of different values of A, but it kind of centered around this zone. So, usually you'll know that your Markov chain Monte Carlo converged if you kind of see this kind of plot. if you see it like always increasing, then that means that, for example, it's always finding that moving increasing a has a higher probability, which means it hasn't necessarily found the most probable part of your distribution yet. But here it's kind of walking around one part of the distribution, which is telling us that it's kind of found the most probable area of our probability distribution. And now you can take the values of A. So you do like A1, A2, A3, this time series of them. You take that whole array and you do a kernel density estimate. And this then tells you what the probability distribution over A is. That, this is the probability distribution of A given the data. So here's the probability distribution of beta given the data. And so it has the mean estimate is where you kind of think the most likely value of beta is. And what we've shown is that with this measurement distribution of a likelihood function, finding these maximum values of finding the maximum values of these posteriors over infinitely many samples, is this maximum value would be exactly the value that you get from a sum squared error optimization, right? But this is now giving you a whole distribution where it says the most likely point for delta is here, but there's also a probability that it's up to 3.5 or to 2.5. We don't have enough data to be able to narrow it down anymore. So this is the sampling approach to probabilistic programming. We're running ODE solvers under the hood and doing this many times, just like an optimization. But instead of just getting out one point that we say is the best, now we get out a whole chain of points that represents a probability distribution. And if we do the kernel density estimate of that chain, then we have a representation of that probability distribution that tells us, the probability that the alpha that goes into our model is this, right? So we're essentially now at the point where instead of having to choose a distribution to be able to get a probabilistic outcome, we can now say, given the data, let's find what these distributions are, and these are plotted are what the program thinks is the most probable probability distributions. So what is the cost of doing Bayesian estimation? Well, every single time we evaluate the likelihood function, we're solving an ODE. So it's quite expensive, right? Because if you want to get, 10,000 points to be able to represent this probability distribution well, then it's going to take 10,000 OTE solves. So you can see that very quickly. You can see that very quickly. This is going to be a very expensive process. But one thing that's really nice about Bayesian estimation is that it's parallelizable, right? So you can say I have theta 1 is 0.5. Now I choose the next theta 2. And then I put this in the likelihood function. I have a probability of accepting it. Then I choose the theta 3. I choose the theta 4, right? So that's one chain. So you can't necessarily parallelize within that chain because knowing theta 3 is dependent on knowing theta 2, right? So that's quite hard to parallelize. But you can run many of these chains simultaneously, right? So you can say chain 1 starts at 0.5, chain 2 starts at 0.5. And what they'll take as theta 2 is already different, right? And they'll do this. And so you can take multiple of these chains, and after you've run multiple chains, you can do the kernel density estimate on the concatenation of all these different arrays, right? So it would be like the same thing as saying, I want to estimate the probability distribution of a squared. I can do I can do the rand n on two different a's, and I can do a of 1 squared concatenated with a of 2 squared. And this is still a representation of the probability distribution of a squared, but I can do this computation independently of this computation, right? And in the sampling process, I can get a full chain of all of my thetas, but I can do multiple chains all simultaneously, and this is called parallelization of the chains. And that is embarrassingly parallel, so you can run different chains on different computers and then can just concatenate all the chains together to be able to get a better probability estimate. So there are things you can do to improve the probability of this, and libraries like Turing.jl do a lot of different tricks to be able to minimize the cost of doing Bayesian estimation, but it's generally very expensive, right? Optimization is giving you 1 point, and so optimization was already expensive enough. But it's now what we're trying to do is we're trying to optimize for a distribution, so we're trying to optimize and get a full function, and so that's going to be necessarily more difficult than just getting the maximum of that function. Right. So that's the Metropolis Hastings algorithm. In practice, when you look at these tutorials, you don't see Metropolis Hastings. You see no U-turn sampler, which is a form of Hamiltonian Monte Carlo. So what's the difference? Why do we not use this version of sampling? And so the reason is because Metropolis Hastings is very easy to implement and motivate, right? So I can say, oh, you want to move towards the higher probability distribution areas. That makes sense. And if you just kind of choose this, if you choose this as your rejection probability, it just turns out that everything works out. You get the right probability distribution. It's a nice, easy algorithm. Now, actually proving that this gives you out exactly, samples according to that probability distribution that you're looking for is much more difficult to prove. But it's at least understood and well motivated, right? But this algorithm itself does not scale well to very high dimensions. So to understand that, you know, understand that, like, the probability of having a value is not necessarily going to be a nice point cloud. So let's say parameters might compensate for each other. So when we look at a model like Lockville-Terra model, right? If parameter P1 is higher, that will increase the amount of U1 in the ODE solution. But if parameter P2 is lower, then that will also increase the U1 in the ODE solution. So you don't necessarily have that all of the, you don't necessarily have a smear of your likelihood. Not everything is probable, right? So, if you have a data point right here, then the probability of P1 being high and P2 being low is equal to the probability of having P2 being high or P2 being high, and you can flip them around, right? So there's these linkages between your probability distributions or between your parameters. And what those linkages cause is in your higher dimensional space that you're trying to find a probability on, your the points where you have a really high probability is not a cloud. It's not all directions are highly probable. Instead, if you have two parameters compensating for each other, then increasing one parameter at the expense of another means that there's like a line in there. There's a line in the higher dimensional space, which is the most probable point, right? So if you have found parameters that go exactly through your data point, you can move parameter 1 up and parameter 2 down. That will also exactly go through your data point. So that's also a high probability parameter. So there's like a line that is, that is a high dimensional, or that is a low dimensional manifold in this higher dimensional space, that is the highest probability line to be on. And that gives Metropolis Hastings a real issue, right? Because let's say we want to do Metropolis Hastings in multiple dimensions here, right? So we say, with theta 1 equals 0.5, 0.5, right? What's our sampling distribution going to be? Well, let's say we do theta 2 is equal to 0.5, 0.5, and let's just do random numbers across each of them. Right, so we just do independent randoms in all directions, right? Let me. So then if we do independent random numbers in both directions, then we're getting points which are centered around 0.5, 0.5. But the issue here is that we know that there's a linkage between our parameters, right? So the probability of going in all directions is not correct, right? The probability of actually hitting a point on this line is really, really low, right? Because what we really want to be doing is saying when the random number is really large here, then the random number should be really small, or negative here, right? Because there's this compensation. So whenever we increase P1, we might want to decrease P2. But just doing a symmetric sampling approach doesn't take into account those correlations. And so the probability that you end up in a very low, within a zone where the likelihood function is very small is quite high, right? Because the probability that you accidentally took something on the line of high probability is very low. Now, what happens with Metropolis Hastings when you take a sample and that ends up in a low probability zone? Well, you have a very high chance of rejecting it, right? But this means that we're going to do a lot of really bad work with the Metropolis Hastings. So, we have a point that's on the line. We take another random point. It has a very good chance of not being on the line. And so it has a very good chance of having a very low probability, which means we reject it. And we take another sample, we reject it. Take another sample, we reject it. And so what you can show is that if you have your highest probability points actually lining up on a lower dimensional manifold, then the vast majority of your steps in Metropolis Hasting are going to be rejections. But every time you do a rejection, you still have to solve the ODE with that chosen set of parameters. So you might need to do, 100,000 ODE solves just to get a chain that does 100 moves. So needless to say, that's going to get very slow. And in fact, as you get higher and higher dimensions, the probability of landing on the lower dimensional space goes lower and lower and actually converges to zero. So the amount of work you have to do with Metropolis Hastings gets essentially infinite in high dimensional spaces. So when you're starting to do things like, oh, I'm trying to sample four parameters that go into my ODE solver, Metropolis Hastings is going to be, like 99.99% of the work is just solving ODEs on parameters that it just throws away the data for. So that is a really not good procedure for doing this. So that's why I emphasize in the notes that it's really slow in high dimensions, right? Because you end up needing to do millions of ODE solves just to get 100 points in a chain. So if you want to get like a good estimate of your probability distribution, you're doing a whole bunch of samples. So what we need to do instead is we need to bias the sampling process, right? We can't make this sampling process be purely symmetric. We need to make this sampling process have a higher chance of giving points that live on the high probability line. So how do we do this? Well, so let's say we wanted to try to follow the line as good as possible, right? So we wanted to take points, right? So we want to sample points such that they have a high probability of going this way and they have a high probability of going this way, but they want to follow the curvature of these lines. So how do we know the curvature of these lines? Well, the curvature of a line can be given by an underlying vector field. Um, so the first idea that you might have is to say, well, the way that we improve optimization, right? Instead of just taking random points, instead of doing optimization with essentially random points, um, we use gradients, right? So what would the gradient of my likelihood function look like? So the gradient of your likelihood function would go to the area like with the mean highest probability. Well, if all of these points have a very high probability, then the most probable point, in the or the point that the gradient would actually point to is not something on the line, is it would actually just all point to the center. So it's a good idea, but it's not quite there. So what we need to do though, what we can notice though, is that the manifold of high probability is always perpendicular to the gradient. So what we want to do is we want to find a way to, if we knew the gradient, then we can sample points by using the points, by sampling in the direction that is perpendicular to the gradient. So we can take the, theta 1 equals this value, and then we can we can solve the ODE, but not just solve the ODE, but use, forward sensitivity analysis or adjoint sensitivities to calculate the gradient. And then from the gradient here, we can try to come up with a way to be able to find the perpendicular to the gradient that's pointing inwards. Um, so that way, and then use that to be able to better sample along the line. So how do we then try to better sample along the line? Well, let's actually look at how this is done in practice. Like, let's look at how this is done in physical systems. How would a satellite that is moving around the Earth stay on this line or stay on that circle with high probability, right? the gradient of the movement for the satellite is moving towards the Earth, right? Because the gravity is always pulling the satellite towards the Earth. So the force is going towards the Earth. Just like the force of optimization is going to try to pull you to the center. So how come the satellite does not just go straight to the Earth? Well, because it has momentum. So what this means is that what we want to do inside of our chain is we don't want to just throw away everything about our previous point. We want to add momentum to the process. And we want to mix that momentum with the gradient to be able to tell us, and if we mix the momentum with a gradient, we should be able to stay on a line of high probability, right? So this is just like an intuitive introduction as to why this might make sense. And so, if you recall from basic physics, you have Hamiltonian mechanics, right? So you have a Hamiltonian, which is the energy. So what we're going to do is we're going to say we're going to relate the energy to our probability. We want to say that the area of high energy is going to, or the area of low energy is the high probability estimate area. What we want to do with Hamiltonian mechanics, though, right? Like what happens in natural systems is you have conservation of energy, and so if you say that this is a high energy point, then you want to have a high chance of conserving energy in your sampling process. And if you conserve energy in your sampling process, then you're going to be sampling other points along this line, and you're going to have a really high chance of only hitting very high probability points. And so if you define the energy here, like if you make this probability be something that's related to the Hamiltonian, then the way that you would conserve energy is to use Hamiltonian dynamics. This is where the name Hamiltonian Monte Carlo comes from. So if I had a Hamiltonian, right, the way that you would change the differential equation for how you would change the point would be given by the derivative of the Hamiltonian with respect to is given by the derivative of the Hamiltonian with respect to p, right? That's just standard Hamiltonian physics. And now the derivative of the sorry, that's missing a thing. The derivative of the momentum with respect to time is given by the minus derivative of the Hamiltonian with respect to x. Right, so here now I'm saying p is the momentum. So we can what let me recap this a little second, right? So if we had a point that was on the high probability line and we had a momentum and we defined a Hamiltonian such that everything on this line was kind of like an equal energy, then using Hamiltonian physics or Hamiltonian mechanics would tell us how we should be changing the momentum and how we should be changing the current point such that we would stay on the high probability manifold. So what that means is we want to make the Hamiltonian then equal to the minus log of the probability distribution, because then the minimum energy, would be the points of the highest probability, right? Why do we want the minimum energy? Well, remember that physical systems always move towards the minimum energy. You're always trying to find the minimum energy when you're trying to do things like simulated annealing and you always assume that electrons fall back to the minimum energy zone, and so these physical systems naturally want to go to the minimum energy line. So we set it up so that way the highest probability line is the Hamiltonian point, the energy point with the lowest energy. And so now what we need to do, though, is if this is our Hamiltonian, we need to choose a sampling distribution, and we need to relate that sampling distribution to the momentum. So, um, so how can we bring momentum into here? Well, so what we can do is we can actually say we don't just have the Hamiltonian given by only the probability distribution. We can have the Hamiltonian given by the probability distribution and another distribution. And so this other distribution is going to be the kinetic energy, right? So our potential energy is going to be set up so that way, our potential energy is the minus inverse of our probability. So that way our potential energy is giving us like a force that pulls us back to this line. And then our kinetic energy is used so that way, if we don't have any kinetic energy, if you don't have kinetic energy, you can't have momentum. So we need to choose a kinetic energy so that way we can have momentum to stay on this line. So this is this is then how you get to Hamiltonian Monte Carlo, right? Where you say I define a Hamiltonian which has a potential energy that is given by my log likelihood, and I just choose a kinetic energy function. The different methods for Hamiltonian Monte Carlo that are all about how do you choose this kinetic energy function. Um, but remember that we need to make a connection back to our gradients, right? Because our momentum, right, needs to be perpendicular to the gradient. So this is where all differential programming is going to come back, because the gradient is going to come into the definition of these kinetic energy functions. And all these different methods for Hamiltonian Monte Carlo are all about how do you choose a kinetic energy function as a function of the gradient of the ODE solution, such that it have a high probability of being on this high probability line. So nuts, for example, is the no U-turn sampler, which is just one choice of how to do this kind of sampling process, or one choice of how to do the kinetic energy sampling. And so this all connects back then to what we did in the previous parts of the lecture, because now what it's saying is that the good forms of Bayesian estimation also need to calculate gradients. So they need to use dual numbers, or they need to use reverse mode automatic differentiation, adjoints, and everything that we are doing before. So, okay, once we have the system, right? So dx dt equals dh dp, and dp dt equals minus dh dx, right? So there's one last detail, right? So if we had a point on here and we had a differential equation that told us how to move along this line, how would you actually solve the differential equation such that you'd stay on this line? So let's say you just did a normal ODE solver with a Hamiltonian equation. So here I say that the initial condition is 1, 0. I use the harmonic oscillator and I solve it with an ODE solver. 1, 0 is going to be the point right here, or right here, right? And you can see that what's actually happening is that this is spiraling, right? So if I actually plot t over time, when I plot, here is the x coordinate, so the second value, it starts at 0, it goes to 1, it's a harmonic oscillator. But if I solve it for a very long time, what I see is I don't keep on going from 0 to 1, it starts diverging out to infinity. The reason is because this ODE solver itself is not an ODE solver that conserves energy. So if you, so what's going on here, right? So we define a Hamiltonian for how to sample such that we end up staying on this point. But if we use a naive ODE solver, we do not necessarily stay on this line if we do a lot of samples, because ODE solvers have their own error, and the error of that ODE solver might bring it to lower energy points accidentally. So in order to have a higher chance of accepting points, we need to choose an ODE solver that has a good chance of conserving energy. And it turns out that the standard methods that we discussed before, we never discussed conservation of energy in solutions. And so, there was nothing about the derivation that made it good for conserving energy. They achieve, O of delta t to the fifth power error, but that all that error might be, it doesn't necessarily mean that you have a low error in your in the actual energy estimate, right? So it could be moving with it could have a very good approximation, but that approximation could still be off on the error calculation. And as you move forward in your simulation, you might be compounding and and getting more and more error in the energy. And so that's actually what we're seeing here, right? That as you solve this harmonic oscillator billions of times, going to t equals 10,000, the energy just keeps on increasing, because the way that the error is happening in this Runge-Kutta method is it's just kind of putting a little bit of extra energy after every single step. And so after 100,000 steps, you get more energy. And so what we need to do, though, is we need to use different ODE solvers on Hamiltonian equations to be able to preserve this kind of property. And so symplectic integrators are integrators that are derived to live on symplectic manifolds, where manifolds defined by Hamiltonians are what are symplectic manifolds. This is a very deep topic, so I'm not going to describe it in full detail, but I'll showcase some results with symplectic integrators. So here, for example, we have an ODE that is defined by a Hamiltonian, um, and so if we actually look at, for example, what the solution is to the ODE with a symplectic method, we see that a very natural signature of this is it ends up being almost perfectly periodic, right? It doesn't exactly conserve the energy, but the energy deviations are quite small, so like 10 to the minus 7, and they have a very periodic nature to the way that they're doing it because the solution will live on a perturbed version of this Hamiltonian. That's what you can prove about symplectic integrators. It's not living on the true Hamiltonian, but it's living on a perturbed Hamiltonian. And so this perturbed Hamiltonian has its own kind of conservation of energy, and so you tend to get less energy variance. So let's actually, and there actually are some things called first integrals like angular momentum, which are conserved exactly by symplectic integrators. It's a common misconception that they conserve energy exactly. They don't conserve energy exactly, but there are quantities that they do conserve exactly. Now, let's. This is on the Kepler problem, looking at a planetary orbit. Let's look at what happens with standard ODE solvers. So this is a Runge-Kutta method. If you're to try to solve the orbit thousands and thousands times with the Runge-Kutta method, what you see is you actually see a linear divergence in the amount of energy, right? That the energy diverges over time because every single time it does a step is going to be adding a little bit more energy air. And so what the symplectic integrator is really doing is it's kind of giving you this guarantee that if you do an integration that is on such a manifold, so that is derived from a Hamiltonian, you're going to essentially get back to the point that you started. And so if you take all these types of different Runge-Kutta methods, so like ERKN, these methods are much higher fidelity, right? They're much lower error than the symplectic integrator, but the error is all biased to be giving it, in this one is giving you lower energy all the time. This one is always giving you higher energy. And so you kind of get this divergence. So even though it is a ODE solver with lower step error over very long integrations, it can be outperformed by a symplectic integrator on this type of problem. Not every problem, but at least this type of problem. So here, for example, is what SIT5 looks like. It's one that you might be familiar with because your homework. And here you can see this kind of same behavior where a standard method will have a divergence in the energy over time because every single time it goes around this loop, right? You can actually see when it goes around this loop, it has the same pattern. Every single time it goes around this loop, it has more energy. And you can actually see that this line is starting to get thicker. It's actually diverging in the way that it's going around. So let's do this with RK4 with fixed DTs, and what you'll see is exactly this behavior, right? So if you take a starting point here, and then you just keep on running around in circles, each time you go around, the RK integrator is going to be moving the energy up a little bit because this integrator on this problem is biased to increase the energy. So if you loop it around enough times, you start to see this divergence where every single time you get a higher and higher energy value. There are other ways to be able to handle this problem. So what you could do is after every single step, you can project it back to the manifold of constant energy. So you can say, I know that my energy is equal to 1, so after this step, let me calculate the energy of my system, and I then divide by the total energy. I divide all my variables by the total energy of the system, and now that gives me a projection back to energy 1, and you could always keep on doing this projection procedure. So there are many different ways to be able to handle having constant energy over long time integrations. Um, and there's a Stack Overflow post that goes into detail about how these methods kind of work and why do they exist and everything. So if you're curious, please follow up on that. But what this really means is that what this really means is that in the end, a the method for how we are doing sampling of Bayesian sampling is defining a Hamiltonian based off of a likelihood function, right? So the likelihood function has an ODE integrator in there, but the way that we then come up with how to choose our next points is using a symplectic ODE integrator to be able to find the points. So Bayesian integration or these probabilistic programming packages, they're actually all using a form of ODE integration underneath the hood. These special ODE solvers called symplectic ODE solvers. But the way that you move beyond Metropolis Hastings is you start choosing these new points via an ODE solver. And so your likelihood has an ODE solver in there, and now the optimization procedure or the parameter estimation procedure has an ODE solver in there as well. So that kind of shows that these OD solvers are pretty pervasive, and that's all I'm going to go into on the sampling procedure. There's a lot more that can be said, right? Because I haven't even defined, how do you do kinetic energy for nuts or adaptive sampling? How do you find out how to get onto that high likelihood point first, right? Like I skipped a lot of details here, but that's because we can do a whole course in probabilistic programming. What I want to move on to is, very, very much earlier in this lecture, I mentioned that there are two ways to be able to estimate probability distributions, right? One is a sampling-based approach, which Markov chain Monte Carlo, Hamiltonian Monte Carlo. These methods are all Monte Carlo approaches, so they're doing sampling. There's a whole nother area called variational inference, and I want to make sure I mention this. So what you do with variational inference is you represent your likelihood function, or you represent your posterior as a function of your likelihood function. And what you then want to do is you want to do an optimization of the latent variables that define your probability distribution. So what's one way to think about doing this? Well, there are many. What's something that represents a function? Well, you can think a neural network represents a function, right? So you can say, I'm going to represent, I'm going to represent, this posterior like from Bayes' rule, right? So I'm going to represent this function right here with a neural network. Um, and now I can always get samples of this by running my ODE solver. This is I can represent my initial condition in or my initial distribution in many ways. But now the question would be find the parameters of the neural network that gives me the correct distribution such that this equality holds. Right. So you can then do an optimization procedure to find the neural network parameters. So that's essentially what variational inference is doing. And ADVI is automatic differentiation variational inference. It's a variational inference method which is doing automatic differentiation and optimization to find the representation of the function. And the way that you do this is they generally look at, so you want to find the right distribution, right? So if I have f of x is a distribution, um, and I want to put a loss function not on points now. I want to put a loss function on distributions. What you can use is you can use the KL divergence. The KL divergence. Let's find a picture of it. The KL divergence. There's a good picture in here if I remember correctly. Nope. So the KL divergence is essentially a measurement on the distance between two distributions. Yeah, so I think that's why I didn't put one in the lecture notes. It's hard to find a good picture of it. But essentially, if you had a distribution here, like think about it as like a mound of sand, right? Like I have a mound of sand here, and the real distribution I want to get is a mound of sand here. It's kind of a question of how much sand do we have to move to turn one distribution into another. Um, and so the KL divergence is something that has a direct definition. So if you actually go down and you look at what the KL divergence is, it's the sum over all points in the distribution of the log of the ratio between the two distributions. Or if it's a continuous distribution, you use integrals. This right here is just a function. But what this is really trying to say is if you represent your probability distribution directly, then you can put a cost function on having the wrong probability distribution as the KL divergence between the distribution that you currently have and the distribution that you should have. where you know what distribution you should have, because Bayes' rule tells you that the distribution you should have is this one right here. Right. And so minimizing something, minimizing things with a KL divergence is quite hard. But what you can choose is that instead of minimizing the KL divergence directly, you can maximize what's known as the evidence-based lower bound, or what's known as the elbow. So maximizing this is equivalent to getting the maximum of the minus KL divergence. That is a difficult proof, but essentially what this comes down to is that you can then say, here I have a probability distribution that I represent with some parameters. So let's say this is my neural network. I have a prior distribution. I can calculate, you know, I can calculate the average probabilities from these probability distributions to define the elbow, and then I can find the parameters that make these distributions the same, or make the elbow 0, and that will give me the parameters that give me the most likely distribution, and then I have a direct distributional estimate. So this doesn't require any sampling, right? Because or this doesn't directly seem like it requires sampling because you're directly representing the probability distributions. But when you actually want to do the gradient estimation for the evidence-based lower bound, you need to do a probabilistic estimate for what the gradient is with respect to each of these latent values, and that turns out to be a average over gradients. So you do an average over adjoint solution. So once again, everything that we were doing with adjoints and dual numbers and differentiable programming will still have to come into play because you need to get gradients of this likelihood function. And there's a whole story to be said about that. And so if you look up the ADVI method, if you're interested in this, you can find a whole lot more details. But essentially, hopefully, that's a nice overview for how something like Bayesian estimation works on something like a differential equation. So you can get, instead of getting point values, you now have uncertainties in your solution, or uncertainties in your parameter estimation, which is all done by either these sampling techniques or variational inference. Where once again, these sampling techniques and variational inference, they're using all these gradients and differential programming that we discussed before, and it's using ODE solvers under the hood to be able to do the sampling procedure. So everything we discuss really comes into play in differential programming, and you can look more if you want to know a lot more details about the process.